So we're going to go through a couple of ideal gas law problems. In this first problem, you have a drum that's used to transport crude oil, and it has a volume of 162 liters. How many water molecules? So whenever you've got something like molecules, you're going to have to calculate moles of the substance. As steam are required to fill the drum at a pressure of 1.00 atmospheres and a temperature of 100 degrees Celsius. So this is my temperature. Automatically with the Celsius, you've got to go ahead and convert that into Kelvin. So that's going to be 373 Kelvin. This is going to be an ideal gas equation. So you're going to do 1.00 atm as my pressure times the volume, which is 162 liters, is equal to moles, which we don't know, R, which is 0.08206 liters over 8 liters times atm over Kelvin times mole times the temperature, which is 373 Kelvin. You're then going to have to isolate the moles, so we're going to divide both sides by R times temperature. So then we do the same on this side. So in our calculator, we're going to do open parentheses, 1 times 162, close the parentheses, divided by, open parentheses, 0.08206 times 373 Kelvin, close the parentheses. And I get 5.29 moles. Now, we're next going to have to convert those moles into molecules. Now, if you remember, to go from, we're going to have to use Avogadro's number. So I'm going to take my 5.29 moles, and to go from moles to molecules, I need Avogadro's number. So 1 mole is equal to 6.022 times 10 to the 23rd molecules. So moles cancel out, and when I multiply this out, I end up with 3.19 times 10 to the 24th molecules. So in this next problem, we have mixtures of helium and oxygen. Anytime you see something with mixtures of more than one gas, you probably should be thinking Dalton's law. They're used in air tanks of underwater divers for deep sea dives. For a particular dive, we've got 12 liters of oxygen. That's diatomic oxygen, O2, at a temperature of 25 degrees Celsius and 1.0 atmospheres. And we've got 46 liters of helium at 25 degrees Celsius and 1.0 atmospheres. And we then take both of these and pump them into a 5.0 liter tank. We're going to have to first calculate the partial pressure of each gas, and then calculate the total pressure in the tank at 25 degrees Celsius. This problem is going to take you a bit of space, so make sure you've blocked out some space for yourself to work with. So far we have the pressure, volume, and temperature of each of our gases, both oxygen and helium. So I'm going to use the pressure, volume, and temperature So first we've got our pressure of our oxygen, which is 1.0 atmospheres. And our volume of our oxygen is initially 12 liters. Our temperature of our oxygen is 25 degrees Celsius, and we're going to go ahead and convert that into Kelvin, so that's 298 Kelvin. We're going to substitute it into the ideal gas equation so we can figure out how many moles of each of our gases we have initially before we put it into that 5-liter container when the two get poured together. So we're going to take 1.0 ATMs times 12 liters is equal to N for oxygen times R, 0.08206 liters times atmospheres over Kelvin times mole times the temperature, 298 Kelvin. We need to then isolate N, so we're going to divide both sides by 0.08206 liters times atmosphere over Kelvin times mole times 298 Kelvin. So we're going to divide both of these by 0.08206 liters times atmosphere over Kelvin times mole times the 298 Kelvin. So that gives us moles of oxygen. So that's going to be 12 divided by 0.08206 times 298, and that gives us 0.49 moles of oxygen present. So we're going to hold that information for a little bit while we figure out the moles of helium that are present. So to determine moles of helium present, we're going to use our pressure, which is 1.0 atmospheres, times the volume of just the helium, that's 46 liters of helium, is equal to the moles of helium times R, which is 0.08206 liters times atmosphere over Kelvin times mole times the temperature, which is 298 Kelvin. So we're going to divide both sides by 0.08206 liters times atmosphere over K mole times the 298 Kelvin. So now your moles of helium is equal to 46 divided by 0.08206 times 298. And I get rounds to 1.9 moles of helium. So now that we know both of these were dumped into a tank that was 5 liters, we know how many moles of each were put into our tank. So we've got a tank, which we now know is a tank that is 5 liters in size. We know that your tank is still at a temperature of 298 Kelvin. And we know that we have 0.49 moles of oxygen and 1.9 moles of helium. So now that we know how many moles of each of these we have and the temperature and the volume, we can use that information to find the pressure of each. So next we're going to find the pressure of the oxygen, and then we're going to find the pressure of the helium. Once we find the pressure of these individually, then we can add those two together to do Dalton's law. The pressure of the oxygen plus the pressure of the helium gives us the total pressure inside of the tank.